In this video, I'm going to talk about the reduction of representations. And so we've been kind of dancing around this issue, but now we want to actually find out what these two matrices are, this unitary matrix U. And so to do this, we need to have it that the representations that occur more than once in our direct sum here are actually identical. And so they'll be transformed by U into identical form. And so this means that we have our direct sum here, which is this large matrix that looks like this, where each of these with the same second index will actually be identical to each other. So the Greek letter subscript tells us which representation something is, which representation it is, and the number distinguishes different sets of basis vectors for that representation. So representations that differ only in the second subscript, as I said, are therefore identical and not merely equivalent. So we have this basis, which I have this E with kind of the two bars over top of it. Other places will use different sorts of ways to represent it, but these are said to be the symmetry adapted basis here and can be understood in the following way. So we have this basis here for the first occurrence. There's the base, the first base, the second base, the third basis, and so on. Then we have this for the second occurrence, and we keep going through that way until we get to the last occurrence of this alpha representation here. Then we start with the beta representation and sort of go through that until we get to the end of that, and then we would start, I guess, on the gamma one and so forth. And so we have that the d alpha 1 is equal to this e sub I alpha 1, where this 1 is where that Greek letter mu would be. So the alpha is the representation that it is. This is the occurrence, and then the I is the sort of basis vector. And so we would say that something that looks like this is the ith basis vector of the muth occurrence of the alpha irreducible representation. And so since representations of different mu's, so the different occurrences are identical, we say that this E sub I alpha mu transforms like the ith basis vector of some standard irreducible representation. So the basis vectors, so a basis vector I of the alpha representation in each muth occurrence of it will transform, all the same way. And so we would say that there is, kind of a standard way that it would transform. Therefore, we say that the pair alpha I indicates a symmetry species of the vector, while mu distinguishes different vectors of the same species. And by the way, I know this is all really abstract sounding, but at the end of this video, I'm actually going to go through an example using our C3v example group. But for now, I'm just sort of laying out the sort of abstract way of thinking about this. So if our v is an arbitrary vector, we can express v in terms of the symmetry adapted vectors. And so we have this symmetry adapted basis here. And so if we write it this way, then on the right side here, we have a component that is the sum of the occurrences of the kth component. And so essentially what we're saying is, we have our vectors here like this. So these are all column vectors, and so we'd have like a v1, v2, v3, and this would be for the first occurrence. Then we'd have a v1, v2, v3, and so on for the second occurrence. And so we are summing over the occurrences, this mu. And so we're essentially taking all these first ones here and summing them together into a single number here, a single component right here. Then when we sum those together, so we actually make a vector out of that. So this is a vector where each component of it is the sum of the occurrences of that single that single component over here. And so the first one would be the first component in our vector would be this. The second one would be the sum of these second ones. The third one would be the sum of these third occurrences, or the third basis vector from each occurrence. And so that's what's going on there. So this is essentially turning every identical component in every occurrence of an irreducible representation into a single number, collapsing the multiple vectors of each occurrence into a single vector. So the left side generates a vector from each of those components here for each irreducible representation, the alpha, beta, gamma, delta, whatever, which act as components for V like this. And so so we have these components here for our V, where each of these vectors here, as I said, are these components right here, which were made from the different, well, the summation of the different occurrences of these vectors here. So these vectors specify a set of basis vectors for a subspace. So if we extract the alpha, so the components from the alpha representation, the basis of a subspace of this symmetry species, then what we have is a projection onto a subspace specified by the alpha I symmetry species. And so a projection is kind of exactly what it sounds like. So if we're in a 3D space like we show here, then a projection onto this 2D plane is just, whatever, however much of this vector here overlaps with the 2D plane right here. And so this red one here is the projection. And so up here, we're just sort of talking about this in sort of a very abstract n-dimensional space, but we're saying that, we have some vector in our, really high dimensional space, but we're sort of projecting it onto just a subset of that space. And so this is a projection. And in fact, in the next video, we will see that we can turn what we're talking about here into a projection operator. So we can actually make it into an operator, but I don't want to get too ahead of ourselves here. So our projection is to be acquired by subjecting our vector here to all the symmetry operations of our point group, and then combining the resultant vectors into a linear combination with suitable coefficients, which can be obtained using this. And we'll actually see that this here is actually part of our projection operator in the next video. So if we just sort of took this part right here, that would be kind of like an operator. There'd actually be a G alpha over G. But anyway, I don't want to get too ahead of ourselves. And so where the D with this funny little thing over top of it is the transpose inverse, called the contragradient or dual representation. So I talked about this in a previous video, but I'll give a little reminder here. So the way we can think about it is we have the inverse and then we transpose it, and this plays a similar role to the dual space of a vector space, and it has this property here where if we take the product of this contragradient with this with this representation here, then we get this right here. So it'll be equal to the order divided by the dimension of the representation, then all these Kronecker deltas here. And so as an example, if we have these two representations here of our C3v group, so these are two this is a non-unitary representation here, and then this is its contra gradient. And if we do this action right here with I equals j equals k equals l equals 1, then we just take sort of the red and the blue one from each of these symmetry operations, add or multiply them and then add them up, and we get 3, which makes sense because we're saying that the order g divided by the dimensionality, which in this case is 2. And so the order of C3v is 6. The dimensionality that we are using is 2, and so that should be equal to 3. But if instead we do I equals k equals l equals 1, but j equals 2, and so we are saying that these are not equal, the j and l, then when we do this operation here, so now we're taking the red, multiplying by the green, and then adding up for all these representations, we get 0, which makes sense. That agrees with this sort of Kronecker delta here, that if the j and l are not equal to each other, then this will be 0. And so that is just sort of, like I said, a reminder of what the dual representation or contragradient is. So when we do our symmetry operation r sub n on our vector here, we are transforming the symmetry adapted basis vectors like this. And so this is saying that each symmetry adapted basis vector here is becoming a linear combination of all the other symmetry adapted basis vectors in the same occurrence mu of the symmetry species beta, with components in the kth column of the matrix representation of our symmetry operation here. And so we see that we're summing over M, and so we're taking each of these basis vectors here and sort of summing down a column in this matrix here. So this is a matrix representation, and so we have, you know, our sort of E1, E2, E3, and so on here, and we are multiplying it by this matrix here, and so we are sort of taking the R1, 2, R2, 2, and so on, going down the matrix that way. And so that's essentially what we're doing. We're ending up with a linear combination of these basis vectors. So each basis vector here is becoming a linear combination of all these basis vectors multiplied by a component that comes out of the elements of our matrix there. And so putting together everything that we've been talking about here, we get these complicated looking things, but we can sort of use this simplified version here. And so we see that I actually put this in the square brackets in anticipation of the next video, where we will have this, and then this will actually sort of move this, so G alpha over G onto this side, and that becomes a projection operator. But anyway, I won't get into that too much in this video. So even though we only have 2 indices on here, we have to think about these matrices here, so the D alpha and the D beta, as 3D matrices, since they also have that occurrence mu repeating each time. And so as such, this summation right here will have a linear combination for a constant I and constant j as we sum over the mu. We then move down to the next I and do another sum over mu. We iterate over all these until we've exhausted all the i's, and then we finally move on to the next j. In this fashion, we end up with a collection of summations over mu that look like, and so I'm making these substitutions, and so this is just to simplify the notation. So we end up with these summations that look like this. And these summations are actually acting as basis vectors for our representation D alpha. So each of them with identical mixture of vectors of a given species. So the summations transform like this, so we act our symmetry operation on this, and we end up getting this sum over k here of our basis vectors times our matrix here. And so we end up with this here, and then these acting as the components of these basis vectors. So we're getting the components out of this matrix right here. All right, so to make this a little more concrete, we'll use our C3v representations as an example. So we have the direct sum of this D1 representation here and this D3 representation here. And so that's just essentially putting these ones here into the bottom corner here and turn these into 3D matrices like this. And so if we set our arbitrary vector v equal to our E1 basis there, then acting with all these symmetry operations gives these transform bases here. And so what I'm doing here essentially is I take the identity acted on E1 and that gives us E1. So we have our E1 here and when we act E on it, we end up with that. But if we act our C3 on it, then E1 ends up here, which is in the E2 position, and so it becomes E2. Similarly, with this, when we act the inverse C3 on E1, then the E1 the E1 ends up down here, which is in the 3 position, and so on with all of these different basis vectors here. So we are acting each of these on our basis vectors. And so for the D1 representation, we have that the contra gradient is just equal to the this representation here, the complex conjugate representation there. And so, like I said, we're acting on our vector there and we're saying that that is E1. But in the 1D representation, we only have the I equals 1, j equals 1 here. And so that only equals 1. And so the summation just ends up being this right here. So we just have 2 of everything. And so I just factored the 2 out there, which gives us a vector normal to our triangle. And so once again, these dashed lines are supposed to be kind of sort of slanted behind it, so they're behind the triangle, sort of slanting into the screen as they go down to the origin right there. And so we're saying that when we do this, we have this new vector here, which is now something that is sort of pointing out of the screen. And so we can see if we sort of took 2 of each of these vectors that kind of point back into the screen and added those up and multiplied it by 2, that we would get something that is sort of pointing out of the screen and sort of normal to our triangle there. So the vector that we have in red here is the invariant subspace in which the D1 representation exists. So we now look at the matrices for D3, and we begin with the I equals 1, j equals 1, and then go through the different permutations of I equals 1 and 2 and j equals 1 and 2. And so when we do that, so we're using our transformed bases here. So the bases we got from these transformations. And so we just take the matrix elements out of these and multiply it by each of these transformed bases here. And so that's all we're doing. So in the 1, 1 position in our matrix, which is sort of this one and this one, so the 1 minus a half, minus a half, and so on, is where we are getting these, the 1 for this, the minus a half, 1, minus a half, minus a half. And so we end up with 2E1 minus E2 minus E3. Then we do the same thing for the 2, 1 position in our matrix, which is sort of this one right here and this one right here. And so we just add up all those along with our transformed bases right here. And so we just iterate that through all of the sort of positions in our matrices there. And so for the 1, 1, we get this 2E1 minus E2 minus E3. For the 2, 1, we get this square root of 3 E2 minus E3. And then for the other 2, we actually just get 0 here. So after being normalized, we end up with these bases here. So these are the bases that we have, which we can sort of write like this. And so these green ones are for the D3 representation bases. And I didn't, sort of measure these out. I just kind of eyeballed it and sort of guessed in my head what those would look like just based on how these different, the E1 minus E2 minus E3 and the E2 minus E3 work out. But we see we have these green ones here making sort of a plane, which is a subspace of our three dimensions, and then this red one up here is our invariant subspace. And so these green ones here are essentially projections into this lower dimensional subspace. And so we can actually take these bases right here, so the E1, E2, and E3, the 2E1 minus E2 minus E3 with the normalization factors in front of them, and put those into a matrix that looks like this. So we have our three E1s on the top, so this E1, and then there's a 0 E1 in that one, and so that's where this 0 E1 comes from, and then the E2s in the second row and the E3s in the third row. And so this gives us the matrix U that was kind of what we said we wanted from the beginning. Remember, we said we wanted matrices like this that would give us a sort of block diagonalized version of this direct sum matrix. And so these matrices, this matrix down here and its inverse on either side of these matrices right here. Well, if we had sort of like mixed matrices where we mix these up and sort of with some other transformation so that we have off diagonals on these, we could then use these unitary matrix, or this unitary matrix here and its inverse, to actually get it back in that block diagonal form. And so, yeah, that is the process of doing that. Like I said, a lot of this was very abstract, and that's kind of the nature of what we're doing here. But it's nice to always see something a little more concrete that we are working with here. So like I said, in the next video, I'll be talking about sort of this as a projection operator here. But anyway, I hope you found this video interesting, and I will see you in the next one.